Hello and welcome to another exciting lecture for stats. In this lecture, we are going to talk about correlation and regression. So there's quite a few learning objectives for this week. So we are now getting to the point where we are going to shift our focus from the theoretical, even though in a few weeks we'll be spending an entire week on the theoretical, but we're shifting our focus from the theoretical into the more calculations. So we are going to be doing more calculation stuff. Calculating things, as you're going to see from these, is going to be a large part of what we're going to be doing. So we're going to look at both correlation and regression here. First, for correlation, you're going to construct a scatter plot. You then need to be able to identify range, direction, and strength of Pearson's R, which is a correlation coefficient. You need to be able to calculate the sum across products and the covariance. You need to calculate R, and then you need to be able to calculate the coefficient of determination and the coefficient of alienation. So you can see there that all of them except that second learning objective are relating to either constructing something or calculating something. Then we'll shift to regression from there, looking at differentiating correlation and regression. Then back to calculating, you'll need to calculate the slope and y-intercept. You'll need to calculate the regression equation and predict y from a given x. And then you'll need to be able to use z-scores with the correlation to predict y from an x. So as I said, you can see here there's a lot of calculation stuff, there's more objectives, but these flow into each other as you're going to see. Correlation and regression is something that, interestingly enough, can be taught at different points in the semester. In some classes, you'll get it at the end of the semester. In some classes, you'll get it between descriptive and inferential statistics. I typically teach it whichever way the book has it. And this class, the book has correlation and regression in the middle, so that's why I'm teaching it in the middle. That being said, there's some things that we're going to talk about in this lecture that are way more advanced than anything we've talked about. I'm not going to have you calculate any of that, but they're way more advanced. They're more advanced concepts. That's because the last thing we're going to talk about this semester is ANOVA. And you guys don't need to really know what that is right now. Just know that regression and ANOVA have overlap in a lot of the ways in which they are looked at theoretically. So that is why it could be at the end of the semester after ANOVA, or it could be now, and I'll just kind of hint at those things and then we'll talk about them on a deeper level when we get to ANOVA at the end of the semester. So what do we do first? Just like a lot of things we've talked about in here, what we do first is we graph it. By putting it in graphical form, we can get a good first look or first idea what is going on. So when we're dealing with correlation, the first thing we can do is draw a scatter plot. Correlation is essentially looking at how two variables relate to each other. Well, if you've got two variables and you've got one individual score on both of those variables, you're looking at how they relate to each other, and you can put one of those variables on the y-axis, one of those variables on the x-axis, plot out a data point for each individual, their score on each of the variables, and you get a good graphical representation of what is going on. So looking at that here, this would be an example of a scatter plot looking at the correlation between temperature and aggression. And each of these are going to be different days. So I said individuals before, but again, remember that the observations can be days, it can be places, it can be people, it can be things. All of these can be your whatever you're observing the variable on. In this case, we're measuring it on days, and we've got the average temperature of the day and the amount of aggression that occurred on a day. These could also be individuals. It doesn't say specifically enough. These could be individuals, and they measured it on the day. So they measured the temperature on that day, and then they had them do an aggression task and see how aggressive they were in the task. But as you can see here, there's a general trend. there's a general trend here that as it gets warmer, aggression increases. So that is one thing to consider, is that this now gives us a graphical representation showing us that there is a relationship apparently between these two variables. And again, and I'm going to talk about this later, just because two things are correlated doesn't mean one's causing the other, but we do have a relationship between these two variables looking at it. It's a linear relationship. As one goes up, the other goes up. How would we go about making a scatter plot then? Well, we follow those rules that we had earlier in the semester for making graphs, but we do it for data points. So let's look at this. We draw our x and our y axes. We've got our x here, our y here. What we need to do first is label them. Label the x and y axes with the names of the two variables. So up here, what do we got? We got x is the number of days that alcohol was consumed. So we've got days. We could even say days alcohol consumed. Or you could just say days. And it looks like x goes up to 20. We'll get to that in a second. On y, it is the score on a 20-point exam. So exam score. If I can write today. So we now have labeled our x and our y axes. We technically don't even need this x and this y here anymore, because we now have them labeled with what they are. Now we need to put the scale on each axis. It looks like both of these scales go to 20. So what we're going to do is we're going to just do 5, 10, 15, 20. Now we could do 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Theoretically, you want all those to be the exact same distance. So now we've got our scales on each of them. Then, for each observation, you need to put the data point that's the intersection of their x and the y score. So for this first student, they got an x of 5 here and a y of 19. So you line those up, and we've got student 1. The next is an x of 10 and a y of 15. So we got something in here. Then an x of 14 and a y of 14. So somewhere in here. Then an x of 18 and a y of 9, so somewhere in here. And finally an x of 20 and a y of 5. And you've got this negative linear relationship. As x goes up, y goes down. And you can see they're pretty close to that line. It's a pretty strong relationship. But this is, again, this is our first step, drawing them out like this. It gives us that first indication of what's going on. This gets us to, what is correlation? So what is correlation in the correlation coefficient? Correlation is that statistic used to express quantitatively, mathematically, the extent to which two variables are related, and it's going to tell us other things. It's also going to tell us the direction of the relationship. So what we're going to use is what is called the Pearson product moment correlation coefficient, or just R. You'll sometimes hear it called Pearson's R, or the Pearson product moment correlation, or the correlation coefficient, or the Pearson's correlation. There's all these different things you can hear it called. Pearson's R or correlation coefficient are probably the two most common you'll use. It's important to note that you can only use this with interval and ratio level data. So if you've got a ordinal level variable, you cannot use correlation. There's actually a non-parametric statistic that you can use that we'll talk about later in the semester, and another one that you can use when you've got nominal variables, which is chi-squared, but we'll talk about that later in the semester. So this gets us to that second learning objective, to be able to identify the range, direction, and strength of Pearson's R. And this is that theoretical learning objective that I was talking about. So Pearson's R it's basically a measure of the relationship between relative measures. So a couple weeks ago, we talked about z-scores and how z-scores are relative measures. They are a standardized score. Well, Pearson's R is basically looking at the relationship between those standardized scores. You don't calculate z-scores as you're going along, but as part of calculating R, you are implicitly calculating z-scores. It is occurring in the background as you're going through it. And that's just because if you don't have relative measures, if you don't have standardized scores, then the scales will be so far off from each other potentially that you're not going to be able to get a reasonable estimation of the relationship. So that's what's going on there. Then Pearson's R ranges from -1 to 1. And scores go from -1 to 0 to 1. 0 indicates no relationship. I'm going to talk about what specifically is going on in between greater than 0 and less than 1, but 0 indicates no relationship. A 1 or a -1 indicate a perfect relationship. As I said, on the next slide, I'll talk more about what a score less than 1 or greater than 1 means, but for now, just note that 0 means no relationship, 1 and -1 mean a perfect relationship. So that is the range. So identify the range of Pearson's R, that is -1 to 1. The next is direction. You can look at the value. If the value is negative, it's a negative relationship or a negative direction. If the number is not negative, so it's positive here, then it is a positive relationship. So that is the direction. And finally, we've got the strength. This is the magnitude. And for strength, the closer you are to 1 or -1. So the farther you are from 0, the stronger your relationship. The closer you are to 0, the weaker your relationship. So that tells you the strength. So you can just look at just getting that number, the Pearson's R number. You can tell the direction of it. You can tell the magnitude of it. You can tell all of that. Let's look more at that direction. So positive is going to be anything greater than 0 all the way up to 1. Positive relationships are where scoring higher on one variable will be accompanied by a higher score on the other variable. So as one variable goes up, as one variable increases, the other variable increases. This is that example a few slides ago with temperature and aggression. As temperature goes up, aggression goes up. A negative relationship, on the other hand, is the opposite. As one variable goes up, the other variable goes down. So as one variable increases, the other variable decreases. And this is that example where drinking and exam scores. As drinking goes up, exam scores go down. So that's just looking at the directionality, positive and negative. I already explained magnitude or strength, and I already explained the range. So let's move on to calculations. So the first step of calculating Pearson's R is going to be to calculate what is called the sum of cross products. Just like the first step of getting to variance was calculating the sum of squares, the first step of getting to covariance, which is what we're going to get with Pearson's R, is calculating the sum of cross products. So you'll recall that the sum of squares was the sum of x minus the mean, the raw score minus the mean, squared. Or if you wrote this out, if you extrapolated it, it would be the sum of the x minus the mean times the x minus the mean. That's where that square comes in. Well, now you're going to see something very similar with cross products. So the sum of the cross products is going to be the sum of the raw x score minus the mean times the raw y score minus the mean. So you see here, that is very similar to this, but instead of those second x's, we now have y's instead. And I will tell you right now, this is the definitional formula. There is an easier formula than this, but this is the definitional formula. Okay, so now you've got your sum of cross products, just like the sum of squares. Well, with when we were calculating to getting to standard deviation, the second step after you got sum of squares was to calculate the variance. And the variance was just the sum of squares divided by n. Well, when you've got two variables, you aren't looking at one variance, you're instead looking at covariance, the variance between the two. So it's in, again, just like sum of squares, you recall I said sum of squares increases as n increases. So to control for that, we just divide it by n. We do the same with sum of cross products. It increases as n increases. So instead of dividing the sum of squares by n, we're dividing the sum of cross products, because again, SSXY from the previous slide is equal to the SCP, which is equal to the sum of cross products. So the sum of cross products divided by n gets our covariance. Our covariance is equal to SXY. Note the XY down there. So SXY is covariance. Now, you do notice that there's a little bit different here. When we did variance, we had it squared. Covariance doesn't have that squared because it's already taken care of in a sense, because we did the x's minus the y's, or x's times the y's, not the x's times the x's. So we weren't squaring it. So we don't have to take the square root of it at this point. We will do something else in order to convert it to a standardized score. So calculating the sum of cross products and the covariance, you can calculate the sum of cross products by taking the sum of the x minus the means, x means, times the y minus the y means, and then to get the covariance, we divide that by n. I'll have an easier formula coming up when we get to the example. But before then, we have to talk about standardized scores. So when we talked about standardized scores with standard deviation, we just got a standardized score by dividing it, and it was essentially a standardized variability. We're not interested in just a standardized variability, we're interested in a standardized score, a standardized relationship. So instead of taking the square root of it like we did with the variance to get the standard deviation, we're going to do something similar to what we did when we got a z-score. You recall z-scores were the raw score minus the mean divided by the standard deviation. Important thing there is that it's divided by the standard deviation. Well, we can get a standardized covariance by taking our covariance, when again, remember, SXY is covariance, and dividing that covariance by the standard deviations of x and y. So this is the standard deviation of x, and this is the standard deviation of y. So you need your covariance, the standard deviation of x, and the standard deviation of y, and look at this. We have our R, our correlation. So calculate R. which is our correlation. You need to get the covariance, which we calculated before. You need to have the standard deviation of x and the standard deviation of y. So you either have to have those given to you or you need to calculate those. And you'll recall, again, that s of x equals the square root of sum of squares x divided by n. And the s of y equals the square root of sum of squares y divided by n. So you need to be able to calculate sum of squares of x, sum of squares of y, sum of squares of xy. Okay, that is the definitional formulas. Let's actually look at that. So the definitional formula, again, are when you map it all out, it's going to be equal to, and you reduce it, and you can reduce it here by doing this. It's equal to the sum of squares xy divided by the square root of, and this, there should be a n here and an n here. It's divided by the square root of the sum of squares x times the sum of squares y. That being said, that's too complex. I always tell you there's definitional formulas and computational formulas. Well, this is one of those opportunities where this definitional formula is pretty complex. The computational formula looks more complex, but it's actually easier to calculate. Why is it easier to calculate? Because what do you need to do this? You need your x column, because you need the sum of x here and the sum of x here. So you need your sum of x. You need your y column because you need the sum of y here and the sum of y here. So you need your sum of y. Here we've got a sum of xy, so you need to do an xy column. You need your sum of xy. And finally, you need your x squared and your y squared. So you need to do x squared and y squared, and you need your sum of x squared and your sum of y squared. And there you've got everything you need to do correlation once you've done that. So if you're given just x and y scores here, you can do all of the steps to get your correlation value, to get your R value, just by doing just the steps that you've been doing already this semester. And this goes back to what I said before at the beginning of the semester. The exams are not cumulative, but everything builds on itself. Well, now you're starting to see that the stuff we learned a couple weeks ago, you need to utilize that throughout the semester. And these types of things right here are things you're going to be using for the rest of the semester. So this formula looks massive. It looks really hard, but you just have to plug these values in, and a bunch of these values are the same things. Oh, and you need an n. You need whatever your n is. So if we had a 1, 2, 3, 3, 2, 1, well, we could, sum of x here is 6, sum of y is 6, 1 times 3 is 3, 4, 3, the sum of xy is then 10, the sum of x squared, which would be 1, 4, 9, and 9, 4, 1, we have 14s. We could then plug those values in everywhere. We plug in 10 here. We plug in 6 here, 6 here. We've got an n of 3, so we plug in 3 here. Again, 6 is here, 6 here. Sum of x squared is 14, 14. And we could actually calculate all of that out now. So 6 times 6 is 36. 36 divided by 3 is 12. That shouldn't be, oh, it's going to be a negative correlation, that's why. So our value up here can be negative. Our value down below cannot be negative. So we've got 10 minus 12, or the top is going to be negative 2. The bottom, we need to do 14 minus 12, because again 6 squared is 36 divided by 3 is 12. So that's 2 times 2. We've got 4 down here, but it's the square root of 4. Square root of 4 is 2. We've got negative 2 divided by 2. We have a final answer here of negative 1. It's a perfect correlation. I set this up as a perfect correlation, but we get an R of negative 1. See, you can already see it's not that hard. It just looks complex. So now that we've got R, the next step is to get R squared. So R is our correlation coefficient. R squared is our coefficient of determination over here. Coefficient of determination. That is R squared. And the coefficient of determination is essentially a measure of the relationship between x and y. It tells us specifically the percentage of variance in one variable that can be explained by the other variable. I love to ask this as a Part A question. I can't guarantee I'm going to ask it this semester, but I love asking this as a Part A question. What does the coefficient of determination tell us? The coefficient of determination tells us the percentage of variance in one variable that's accounted for by the other variable. And all it is R squared. You take your R value that we had on the previous slide and you square it. In our previous slide, we had negative 1. Negative 1 squared is negative 1, or it's 1, so it's still the same. But if, let's say, we'd had a negative 0.9, well, we'd square that and we'd get an R squared of 0.81. The last thing to look at relating to that is this coefficient of alienation. And the coefficient of alienation is the opposite of the coefficient of determination. It is the percent of variance in one variable that cannot be explained by the other variable. And its formula is 1 minus R squared. If you take the coefficient of determination and the coefficient of alienation and add them together, you're always going to get 1. Because the coefficient of alienation is just 1 minus R squared. Let's do an example. A little bit bigger of an example and not as exact, not going to get 1 as our example. But let's do this example real quick, looking at this. So first thing we need to do is get our sum of cross products. And I'm going to write here, even though the stuff is here on the slides, I'm going to write on here. You can get the slides which have the answers to it later. Actually, I'll probably delete the answers on this just because it'll be too confusing. So you guys won't see the answers on this, but you'll be able to grab the slides and see the answers already typed up there. But you'll recall that the sum of cross products, SSXY, equals the sum of XY minus the sum of X times the sum of Y divided by N. So what do we get here? Well, I already did all the math over here. So let's just plug in values. We've got our totals, which are our sums. We're looking for the sum of XY. Sum of XY is 28. So we've got 28 minus our sum of X is here, it's 13. Our sum of Y here is 14. And our N equals 4. So if you do 13 times 14 divided by 4, you get 45.5. So it's equal to 28 minus 45.5, which is equal to negative 17.5. We can already tell if our sum of cross products is negative, our relationship is going to be negative. If our sum of cross products is positive, our relationship is going to be positive. And you can look over here and see that as x is increasing, as it's getting larger, 1 to 2 to 3 to 7, y is decreasing. It's going down, 7 to 4 to 2 to 1. Okay, next we got to find sum of squares x. You'll recall that sum of squares x equals the sum of x squared minus the sum of x. That value squared divided by n. Well, we've got a sum of squares x, or a sum of x squared here of 63, a sum of x of 13, and an n of 4. So we get 63 minus 42.25, or 20.75. The next is sum of squares y. Again, sum of squares y equals sum of y squared minus the sum of y. How about we use y? Sum of y squared minus the sum of y, that value squared, divided by n, which is again equal to, now sum of y squared is 70. The sum of y is 14. That value squared divided by 4, we get 70 minus 49, because 14 squared divided by 4 is 49, which equals 21. Now we have everything to get our to our covariance, and from there we can, and also to get to our R value. So now we take those values and we need to calculate the correlation coefficient. So we had a sum of cross products of negative 17.5. We had a sum of squares x of 20.75 and a sum of squares y of 21. If you do the math there, you get negative 17.5 divided by 20.8746, which equals, when you divide that out, negative 0.8383. If we wanted to do that down to 2 decimal places, we'd do negative 0.83. You notice I didn't put a 0 before the decimal point. That's because you do not put a 0 before the decimal point if that value cannot go over 1. If it can go to 1, that's fine, but it can't go over 1. And since R, again, this is our correlation coefficient, R cannot go over 1 or below negative 1, then it is not something that we put the 0 before it. Next, we're going to calculate the R squared. So calculating the R squared, it's just we're going to take that negative 0.8383 and square it. So we get a 0.7028, or R squared equals 0.70. And finally, we get our coefficient of alienation, which is 1 minus R squared. So 1 minus 0.7028, which equals 0.2972, which equals 0.30. And that is all of our values there. Very briefly, want to hit on how to calculate R if you have z-scores. We are not going to do this, but I want to show that if you have a z-score for x, and you have a z-score for y, and you have your n, and you've got to have z-scores for every x score and z-scores for every y score, you can take and sum the x times the y z-scores, divide by n, and get your R. So it's another way to get your correlation. Next, I want to talk about something very important when we're talking about correlation. And that is, to this point, we've been talking about correlations as if they are the only type of relationship that two variables can have. And specifically, we've been talking about linear correlations. R is a linear correlation, meaning those two variables have to have a linear relationship to basically come up with a good R value. You could get a 0 value, and getting a R value of 0 does not mean that there is no relationship. It just means that there is not a linear relationship. Specifically, you can have nonlinear relationships or curvilinear relationships. And since Pearson only examines linear relationships, if you've got something like this relationship that you're seeing here, it would indicate that there's no correlation between these two variables. So no correlation does not indicate no relationship. Specifically here, you've got anxiety and performance. That is that at low levels of anxiety, you tend to do poorly on your task, and at really high levels of anxiety, you tend to do poorly. That's because at high levels, your anxiety is causing you to freeze up. At low levels, your low anxiety is causing you to not practice, not study, not do whatever it is that's going to prepare you for whatever it is, the task. Whereas a moderate amount of anxiety up here, that results in relatively high performance because the anxiety that you have drove you to practice, it drove you to study, it drove you to get ready, so you end up doing better as a result. But this is a curvilinear relationship. It's not going to come up with Pearson's R. Another related thing is that correlation does not imply causation. I said this already before. I'll say it again. This cannot be said enough in stats, in methods, in just science in general. Correlation does not imply causation. Just because two things are correlated does not mean one is causing the other. We as humans want to attribute causation to the world. We see two things happening close together temporally, and we automatically assume one is causing the other. This is why the fear of childhood vaccines is so prominent, and there's so many anti-vaxxer moms and dads, but is because this thing that occurs, that is, that childhood vaccines occur temporally close to when autism symptoms start showing. Shortly after children get vaccines is the age of vaccines is the age where autism symptoms start showing. However, in studies with millions of participants, they've found that the chance of getting a child getting autism is the same whether they have been vaccinated with the MMR vaccine or not. However, because they happen temporally close together, a lot of people attribute that. Plus, there was a doctor who basically spread misinformation, mainly because he had the competing vaccine. So it was in his best interest to get people to stop taking the MMR vaccine because then they would take his. That's all beyond the scope of this class. Just the point is our minds want to see causation. We can't do that though. Just because two things are correlated does not mean one is causing the other. Some examples here: social status and health. They're correlated. However, one is not causing the other. There's likely a third factor in there, just like self-esteem and academic achievement. There's third factors that are likely what's causing those. It could still be in both of those that X is causing Y. So X could be causing Y. It could be that Y is causing X. But a lot of the time, correlations are actually that a third factor is causing a change in both X and Y. This gets us to the second half of the lecture, which is regression. So now the learning objective is to be able to differentiate correlation and regression. Again, this is more on the theoretical side. Correlation describes a relationship. So correlation describes a relationship. It describes how strong the relationship is. It describes the direction of the relationship, that type of thing. So direction and magnitude. Regression, on the other hand, predicts. There's that big word, predicts. Regression predicts future occurrences. It uses past information to draw a prediction line. Those lines I've been drawing through those scatter plots, those are what's referred to as the line of best fit or the prediction line. It's the regression line, but it's the prediction line. And it is used to make predictions about what a score on a variable will be given a score on the other variable using past information. That gets us to our regression equation. And the regression equation is a formula you should recognize right off. It's an equation you should recognize right off. And that is, we used it earlier in the semester when we were talking about, is a transformation linear or not? Well, this was the equation that we used to determine if it was. And if a and b were constants and b was not 0, then this is a linear transformation. But so it's a linear equation. The regression equation is a linear equation. So first things first, we're going to use y prime or y predicted. It's the y with the little apostrophe next to it. It basically means that is a predicted y for a given x. And you'll recall that x and y values are, there's an x and a y value for everyone. Well, once we've got this regression equation, if you take a specific x value, you will get a expected or predicted y value. And then within this, you see the b, which is the slope. We'll talk about that in a minute. And then you've got the a, which is your y-intercept. And we'll also talk about that in a minute. This gets us straight to our 7th learning objective, which is to calculate those two things, the slope and the y-intercept. Let's talk about the slope first. And what is the slope? The slope is very easy to explain what it is. The slope is for every increase in x of 1 unit of x. So if x goes up 1, how much does y increase? And you'll find if the slope is negative, then y decreases. So in that case, it's for every 1 increase in x, y decreases by that much. So a positive y means an increase in y, a negative y means or a positive slope means an increase in y, a negative slope means a decrease in y. We can determine our slope by taking our correlation, our r that we just calculated, and our standard deviation of x and our standard deviation of y. However, there is easier formulas. This is the definitional formula. You can take into r times the standard deviation of y divided by the standard deviation of x, or you can do the SSXY, which you recall was the sum of cross products divided by the sum of squares x. That is another way to do it. So you see the formula here, and you'll notice already that if we're just doing our sum of cross products divided by our sum of squares x, I had computational formulas for both of those to make those easier, so you can just take and do that. And here's the other thing. If you've already calculated r, you've already had to calculate this and this. You already have those wrote down. So if you've already calculated r, you don't have to do anything else except plug in your sum of cross products and your sum of squares x, and you'll get your slope from that. So that's something that makes it easier. Once you've already calculated r, calculating the slope is simple. But let's look at an example. Let's say if our r is negative 0.72 and our standard deviation of x is 2 and our standard deviation of y is 1.63. Well, we can plug those in. We do negative 0.72 times 1.63 divided by 2, and we get a slope of negative 0.58. You'll notice there is a 0 here. Why is there a 0 there? Because your slope can go up beyond 1. It can go below negative 1 and above 1. Whereas up here for the r, there is not a 0 before, because again, the r can never go above 1 or below negative 1. So that is the basics of the slope. But now let's do the computational formula. So we just talked about the definitional formula. Well, let's plug in the sum of cross products. The computational formula for the sum of cross products was that sum of xy times the sum of x minus the sum of x times the sum of y divided by n. That's the sum of cross products. The sum of squares x is down here, the sum of x squared minus the sum of x, that value squared divided by n. But you'll recall again that when we calculated r squared, we calculated this and we calculated this. So on your paper, you'll already have those calculated. It's just a matter of finishing it up, plugging those values in. Then the other half of calculating the slope and the y-intercept is to calculate the y-intercept. Why do we calculate the intercept last? Because you'll see right in the formula, the slope is in our formula. So you have to calculate the slope first. And then it's easy. You just do the mean of y minus the slope times the mean of x. So you need the mean of y and the mean of x. But if you recall, the mean of x is equal to the sum of x divided by n, and the mean of y is equal to the sum of y divided by n. Well, from before when we calculated r, we got the sum of x, we got the n, we got the sum of y, and we got the n. We got all those values. So again, you already have all these values. It's just a matter of plugging them into the formula. And what is this? What is the interpretation of what the y-intercept is? The y-intercept is where the regression line crosses the y-axis. It is what y is when x equals 0. So if you have here let's say we did a correlation like this, well, it's where it crosses the y. This is an x of 0. This is our x-axis. This is an x of 0. So it is what y is when x is 0. And it can be negative. So an example here, if we had it like this, this is where it would cross. So it would be a negative y value. Let's now look at an equation. So let's calculate this. We're going to calculate this by doing all of the steps here. We'll start with the slope. And these values, if you download the slides, you'll see all of this that I'm writing on here already. But let's start with the slope. So with the slope, we've got the slope is equal to the sum of cross products divided by the sum of squares x. Well, the sum of cross products was the sum of x, y, minus the sum of x, that times the sum of y, divided by n. All of that divided by the sum of squares x, which is sum of x squared minus the sum of x, that value squared divided by n. We plug that in. Well, sum of xy, we've got it up here. It's 1023, so we've got 1023 minus the sum of x is 67 and the sum of y is 72. So we've got 67 times 72 divided by our n equals 5. All of that is divided by the sum of squares x. The sum of x squared is right here, 1179, minus the sum of x, which again is 67, that value squared divided by 5. If we do a little bit of math, we get 1023 minus 964.8 divided by 1179 minus 897.8. Do a little bit more math, we get 58.2 divided by 281.2, or we finally get a slope of 0.2070. I'm going to go to 4 decimal places on the intermediate steps and then round to 2 decimal places for my final answer. The next is the y-intercept, and you'll recall there that that is equal to the mean of y minus the slope times the mean of x. Well, we need to get mean of y and mean of x, so the mean of x is equal to 67 divided by 5, which is going to be equal to, what is that, 13.4? No. Oh, I did, yep, the mean of x is 13.4, yes. But the mean of y is equal to 72 divided by 5, which is 14.4. So what we've got here is 14.4, 4 there, minus our slope, which is 0.2070 times the mean of y, which is 13.4. Doing a bunch of math there, you'll get the 11.62 as your final answer for the y-intercept. That means this is crossing the y-axis when x equals 0. It's y is 11.62. Now, we've got our slope, we've got our y-intercept. Now we need to calculate the regression equation, and then from there, use an example to predict a y from an x. So let's first do our regression equation. You are required to do this on your homeworks and exams. So it's going to be y predicted is equal to, you'll recall it's equal to a plus bx. But what we need to do is plug in values now. So y predicted is equal to a is 11.62 plus 0.21x. And again, like I said, I was going to round to 2 decimal places when I got done. So this is our regression equation. Now let's actually use this regression equation to predict a y from a given x. Let's do a given x of 6. So what we would do is we would take this y predicted for a given value of 6. So x is going to be 6, and we're going to plug in 6 into this formula in place of x. So we've got 11.62 plus 0.21 times 6. And if you math all that out, you get 12.88. So what you're saying here is that if x is 6, y is predicted to be 12.88. I said this before, but another name for the line of best fit is called the regression line or the prediction line. There's various different ways to do it. However, one thing to be aware of is there's always going to be error. I used an example earlier of a perfect relationship, but you're never going to find that in the real world. You're never going to find a perfect correlation, a +1 or -1. You're only going to ever find it theoretically on paper. Because the line has to be straight, distributions are almost never perfectly straight. So what to consider there is the error, which gets us to some theoretical stuff. I'm going to say right now, the stuff that's on these next few slides, let me just look ahead. The stuff that's on all of the slides up through the last 2-3 slides. So the stuff that's on the next 5 or 6 slides is all stuff that you do not need to know how to calculate. This is stuff I told you that there's a big overlap between regression and ANOVA. This is that overlap. This is the stuff that we'll cover more when we get to ANOVA at the end of the semester. I just want to kind of preview it now. It's good to know. It'll help you know the stuff better later. So what we've got here is we've got, let's say we draw a regression equation through here. And we've got that regression equation. What you're going to have is 3 different values. You're going to have the actual y value. Let's look at this one here. You've got the actual y value. This is your y value. Then you've got the predicted y value for that x. So you see that that y value is at an x of 5 down here. If we look where on the regression equation we predict the thing to be, if an x is 5, we get our predicted value. So this is our y predicted. And then you've also got the mean. The mean of y, it matters, but the mean of y is in here in the middle. It's just your average y. It doesn't mean much for the regression equation, but it will mean something for when we're talking about basically error and regression and residual and all that. But for every single given y point, for every single y point, for every single blue dot you see here, there's going to be a y value, a y predicted value, and a mean. You can see here on this one, it's pretty much on the line, so the y value and the y predicted value might be the same. But even then, the mean is up here a little bit, so it's above it a little bit. So at no point here are all 3 the same. You're going to have variability throughout. This gets us to pieces of variation. So your variation total, which is also called your sum of squares total. This is the first chance you're going to get to see sum of squares broken down. So we calculated sum of squares for this. That is our sum of squares total. But you can actually break sum of squares down into two components. And we're not going to do it here. I'm just explaining what you can do. In ANOVA, you will break down your sum of squares into these two components. And these two components are the sum of squares regression and the sum of squares residual. And what is this sum of squares regression and sum of squares residual? Well, the sum of squares regression is the variability explained in our equation. There's always variability. The explained variability is our sum of squares regression. The sum of squares residual is our unexplained variability, or another term for this is error. This is our error because it's unexplained. And through this, we can take and calculate things like, since the sum of squares total equals the sum of squares regression plus the sum of squares residual, we can look at all these formulas. Now, this is just, again, way too much for you guys to calculate right now, so don't worry about these formulas. I'm not going to make you do them at all, but we can get and utilize these formulas together, and then through that eventually get to the standard error of the estimate. And the standard error of the estimate is just like when we were calculating the standard error of the mean earlier. It's basically the standard error around the regression line. And also you see here that for the population formula, it's divided by n. For the sample formula, it's divided by the degrees of freedom. In regression, I can spell today. In regression, degrees of freedom equals n minus 2, which is exactly what you see right here. This also allows us to calculate our R-squared another way, just by doing the sum of squares regression divided by the sum of squares total. I told you before, the sum of squares regression is the explained variance. A ratio of the explained variance to the total variance is R-squared, or your coefficient of determination. A ratio of your unexplained variance, which is your sum of squared residual, to the sum of squares total is 1 minus R-squared, or that coefficient of non-determination, coefficient of alienation we calculated before. So this is another way to calculate your coefficient of determination and your coefficient of alienation. I do not recommend it. I'm just kind of showing the theoretical what's going into it here. All right, one last topic, and this is our last learning objective. Use z-scores with R to predict y for a given x. This is a very easy equation to do. One of the easiest equations you'll do all semester. There's one non-parametric equation we'll do later that's even easier. But if you've got a z-score for your x, and you've got an R, a correlation, you can get the predicted y z-score. And because you know formulas, if you know the mean and standard deviation, you can then convert that predicted y-score to a raw score. And if you know the mean and standard deviation, you can take a raw x-score, convert it to a z-score, use this with the R, and calculate a predicted y-score. Let's use an example of that. So an example is if we have a R of 0.8, we've got a z-score of -2. Well, again, going back, it's the z predicted y is equal to our zx times r. So all we have to do is do -2 times 0.8. -2 times 0.8 is -1.6. -2 times 1 is 0.8, or 0.8 times 1 is 0.8. 0.8 times 3 is 2.4, and 0.8 times -0.5 is -0.4. How about instead if we had an R of 6? Well, -2 times 0.6 is -1.2. Then we've got 0.6 and 0.18 or 1.8. These have zeros in front of them. Same with this. So 1.8 and negative 0.3. And let's say we had a mean and a standard deviation. Let's say we had a mean or a y mean. A y mean equals 1 and a standard deviation. The standard deviation of y equals 0.5. Well, now you can just plug in one of these predicted scores. Let's use one of the easy ones, like 0.8, and you could just plug it into that equation. I'm not going to make you guys do that. You guys are probably burned out already. I'm not going to make you guys do that, but just pointing out that it is something you can do. What if they're correlated 0.4, negative 0.4? So negative 0.4 is interesting, so we have a negative value here. So we're going to have to convert negatives to positives. So the last thing is negative 2 with a negative 0.4 is going to be 0.8. We're at positive. At 1, it's negative 0.4. At 3, it's negative 1.2. And at negative 0.5, it's going to now be positive 0.2. And I just did that by taking the r and multiplying it by each of these. So a lot there. This was a really long lecture, or it seems like a long lecture just because there's a lot of information. But hopefully now you can construct a scatter plot. You can identify range, direction, and strength of a Pearson's R just by giving the value. You can calculate the sum of cross products in the covariance. Then from that you can calculate R. Then from that you can calculate R squared, the coefficient of determination, and the coefficient of alienation, 1 minus R squared. Then talking about regression, you should be able to differentiate correlation and regression, calculate the slope in the Y-intercept, calculate the regression equation, and predict a y predicted for a given x. And finally, you should be able to use z-scores to predict y for a given x. Thanks, come on back.